into the class. We have a lot of material to do. Let me share my screen. So remember, guys, I'm trying to do a lot of videos for you. So I've done the videos for GARCH models. Please review them. I will do a very quick review now, very quick. But I'm trying to be as explicit as possible so you can follow the videos and do the EViews file and take notes, etc. It's like a class, okay? So remember that GARCH models, let me write this one here. So remember that the model has two components, okay? One component is what is called the conditional mean. Okay, so what is the conditional mean, guys? It's basically what we have been doing up to now, the ARMA type model. So remember, if it's an ARMA type model, we said this can be something like yt equals mu plus psi1 yt minus 1 plus psi2 yt minus 2 plus ut plus theta 1 ut minus 1. How do you call this model here? Guys, how do you call this model here? This model, guys, is called the ARMA. What is P and what is Q? Remember, P represents the number of lags of the endogenous variable. So I have 2 lags. How many lags of the errors? I have 1 lag. So this is an ARMA 2-1. Got it? Now remember always that the mu is going to be a zero mean white noise process. Okay. So what we have been doing up to the previous class, guys, is simply try to model the conditional mean. Okay. So I want to understand what is the value of y given its own lags, and you can add also here regressors, x regressors. Now, the problem with this model, and if you remember, guys, what we were assuming in this model is that the variance of the errors is constant. So basically, we were assuming this type of errors. Do you agree? So basically, the variance is exactly the same. If you take an interval somewhere, if you take this interval here, and then you compare with another interval, same size, the variance is going to be also the same. Okay, so this is an assumption that we have been doing in the conditional mean. And as we saw, guys, the problem with this assumption is that it's not satisfied in real life. Okay, at least with financial data, we don't satisfy this issue. So what we observe in the data is something that is called volatility clusters. So what is volatility cluster? So the market tends to be, when the market gets nervous, it gets nervous. When the market gets quiet, it gets quiet. And then suddenly it starts again, the people get nervous, and then something like that. So these periods of going up in volatility, down in volatility, up in volatility, down in volatility, this is what is called a volatility cluster. Okay, and this is what we explained last class. Now, how do we model the volatility cluster? Remember, the volatility is not part of the conditional mean. So what we need to do is we need to improve the model of the conditional mean with something that is called, we need to model the conditional volatility. Okay, and the model that allows us to work with this stuff here, with this type of behavior here, is ARCH or GARCH type models. Okay, so let's do a GARCH PQ model. Okay. A GARCH PQ model, guys, looks like, okay, so I will do, normally when you present a GARCH model, you present a complete set of data. So you present a conditional mean. So let's assume that my conditional mean is an AR1, for example. I will do simply assuming that this is an AR1 plus UT. So remember, this is my conditional mean. And I'm assuming that my conditional mean, guys, for this example is an AR1. Okay. What we are going to define, how do I model a conditional volatility? Well, the conditional volatility, I will define the conditional volatility as sigma square mu time t plus alpha ut minus 1 square plus beta sigma square t minus 1. Okay, so this ut is this one here. And this model here, guys, is what is called the GARCH 1-1. Okay, and what we have shown to you guys in the previous videos is that indeed the GARCH 1-1, it's very parsimonious model, so it only has three parameters. The GARCH 1-1, guys, is equivalent, guys, to an arch of infinite lags. Okay, so instead of using an arch with a lot of lags, you simply use a GARCH 1-1, and the model is going to be much better behaved and easier to understand and good to forecast. Okay, so this is my conditional variance. This equation here is my conditional variance. Now, there is something that is called the long-term variance. Basically, when the variance doesn't change anymore. So this is going to be called sigma squared, not the t here. If you see no t, implies that it doesn't change in time. And this one here, guys, is simply equal to 1 minus alpha plus beta. Okay, so this is a very important term. It's my long-term variance. And my long-term variance is simply equal to the constant omega divided by 1 minus alpha plus beta. Now, we have, when we talk with these models, guys, we have negative constraints. So remember, we're talking about volatility. So you agree? So volatility or variances can never be negative. So this implies that I need to be sure that all my coefficients here are all of them larger than 0, are all of them positive. Okay, so this is the first set of constraints. And the second set of constraints is related to this long-term variance. And that one here is called stationarity condition of time series models of conditional volatility. Constraint. And what is my stationarity constraint, guys? Simply that alpha plus beta should be strictly smaller than 1. And you can see that. Take a look. If alpha plus beta is smaller than 1, so and W is and omega is positive, so this number for sure is going to be positive. If alpha plus beta is larger than 1, so we have a negative number here, and so we are going to have a variance that is negative, so it cannot hold. Okay. And then how do we select the number of lags? As we usually do, guys. How do we select number of lags? What do we use? We use something that is called the information criteria. You need to review this, guys. It's going to be part of the quiz. So we're going to have the Kaik information criteria, the Bayesian information criteria, or the Hanna-Quinn information criteria. Okay, so we have these three. We use this as we use for the ARMA models. Simply we use EViews and we select basically the one that is minimum. Okay, so in order to select the order, I mean GARCH 1-1, GARCH 1-2, etc. Okay, so let's do this very quickly. Okay, take 1 minute to copy. Let me open my file.
Professor, just a note, all the eView files that you use on your videos over the weekend that you send us, we don't have those eView files.
You don't have them?
Oh. We don't have, you never send it to us.
Yeah, so you know what? Let me send this to you. Copy, and then let me send this to you guys. Give me 1 second. I will do this right now. Okay, here we go with one. well, today model is going to be this one here. Okay, guys, I have sent you the GARCH model. I have sent you the GARCH model. So can you please open the one that says GARCH? No, this one. Can you please select, can you open the file GARCH models? So this is the one that I have used for GARCH models, okay? Very quick, guys. Ready? So one of the things that you need to remember, guys, all these models, the ARMA model, the GARCH model, and the VAR model that we're going to start seeing today, all of them need and require stationarity of the data. Okay? So the data must be stationary. Okay? Just remember that, please, guys. The data must be stationary. Okay, so my data that I have here, it is the SP500 data. Just be sure that you have SP500. When you click, guys, in the sample, just double click on the sample. When you write arroba all, so it will put all the sample size. Okay, so you can see here, this is my data. Obviously, my data is non-stationary. Do you agree with me? Clearly, it's non-stationary process. So how do we work with an stationary process, guys? Well, one way of doing that is simply computing the D log. So if you see the data. So you see, we simply take the returns, log returns. And we know that is generate RSP, D log SP, and then you get this data. Now, if you take a look to the data, you can see this definitely looks stationary, right? It doesn't look like that, so it looks stationary. Now, you can see here, you see, guys, that, for example, in this part here, the volatility cluster appears. So you have periods of high volatility, periods of low volatility, and then suddenly periods of high volatility, periods of low volatility. It's like going up, going down, going up, going down. And this appears in the market every single time, guys. You can see even intradaily, this appears like that, okay? So we see that this looks like a stationary process, but I showed you last time how to find the arch processes, and indeed you have an arch process here. What we can do now, guys, is let's create a GARCH 1.1 model, okay? So I've just created this model here. If you go quick estimate, we can do this from here. So you do quick estimate equation. And then we go arch heteroscedasticity. Okay, so that's the way you do you create the models for GARCH. So I do this again. If you want to create your GARCH model, you simply go quick estimate equation. Then in the method you look for arch. You see that? So it's quick estimate equation. Then you go to the method and select arch. And then here, what we can argue is that my dependent variable, so my dependent variable is going to be RSP. I want to have the constant, and I want to have the AR1. So I believe that my model, you can do the test here, guys. It's like working with ARMA models. So you need to check first, what is the ARMA P and Q? You do the information criteria, etc. You can do that later. I'm assuming that it's an AR1. I'm just assuming it's an AR1. And then what I want to do is I want to run in my conditional mean a GARCH 1.1. Yeah, so this is already by default GARCH, arch, and GARCH. So what is my arch? My arch component, guys, is this part here. And this is my GARCH component. Okay, that's what EVUs call arch and garch. So if I want a 1-1, so this is the way you do it. This is a garch 1-1. Okay, you then simply run and obtain your model. All of them highly significant, so you are modeling correctly your conditional mean and conditional variance. Later, guys, you can do the forecast. You know how to do that already, so you can do whatever you want once you have this regression, right? There are a couple of things that I need to show you that are really important here. Questions about how to do this stuff? Perfect. So now let's do a couple of things that are really important and a lot of applications in real life. The problem with the GARCH 1-1 model, guys, is that the responses are symmetric. So this implies that if you have a good news and bad news of the same magnitude, your response is exactly the same. Okay, you as an individual, imagine making a 2% up versus making a 2% down, your response is going to be exactly the same. Okay. However, this is not right, guys. What happens is that when you have a gain and a loss of equal magnitude, what happens is that you react more to negative news than to good news. Right? So we are risk averse by nature. Of course, there are some guys that are more risk lovers, but by nature, human nature, guys, we are risk averse. Okay, so if we have a 2% up versus a 2% down, we panic in a 2% down. So our reaction is stronger when we have this 2% down. Right? So this is what is known as a leverage effect. Okay, so leverage effect simply means losses have more impact than gains. Okay, I'm talking about the same magnitude. Okay, so we have two models that control for that. One model is called the Ggr model. Also called the threshold model. Okay, so G, I think, is Glosten. Jagannathan and Runkle. Okay. And their model is extremely simple. They simply use dummy variables to capture these asymmetric responses of individuals or traders. So their model, guys, is the same. So the GARCH model looks exactly the same as before. So we have our omega plus alpha ut minus 1 squared plus beta sigma squared t minus 1. And they add a factor, a gamma factor. Okay, and the gamma factor is going to also have ut minus 1 squared, but it's going to have an indicator it minus 1. This indicator it minus 1 is a dummy variable. So it minus 1 is going to take the value of 1 and 0. So 1 if mu t minus 1 is negative, and 0 otherwise. Okay, so we have been using D for the dummies. In this case, is IT, so it's information at time minus 1. Simply, it's going to be 1 if ut minus 1 is smaller than 0. So it's a negative. If the shock is negative, so it implies negative news, bad news, right? Losses. So what we want to see is if bad losses, if bad news or bad results influence you more than good news. Okay? So leverage effect, guys, implies simply that when losses are present, the volatility should be larger. When gains are present, the volatility should be lower. Right? So now let's take a look to what happens. It's like a dummy, any dummy equation. So take a look to what happens. Okay, so this is going to be my main equation. And then what happens? Let's do what happens if the error in the past, in the error yesterday was negative. So we have bad news, right? So what happens when IT minus 1 is smaller than 0, guys? IT minus 1 is going to be what? It's going to be 1, right? By definition. If I have a negative shock, my information criteria is going to be 1. Now, if it's 1, so what happens with 1? 1 is going to become sigma squared t plus omega, equals omega plus alpha ut minus 1 squared plus beta sigma squared t minus 1 plus gamma, so this number now is 1, ut minus 1 squared, correct? I will put here on purpose the 1 because it is this one here. Then you can see that this factor is exactly the same as this factor. So basically sigma squared t is going to be then equal to omega plus alpha plus gamma multiply ut minus 1 squared plus beta sigma squared t minus 1. You see that, guys? Now, based on this, if we believe that leverage effects happen, if leverage effects really exist, so gamma should be what? Gamma, of course, should be significant, statistically significant. And what should be the sign of gamma, guys? Positive or negative? Remember, positive. Leverage, exactly. Leverage effect implies that the volatility increases when you have bad news. Right? So if we want this to be a larger number than alpha, so this implies that this number should be larger than 0. Correct? Guys, make sense? Okay, so if you have a number that is larger than 0, so alpha plus gamma is going to be larger than alpha, of course, and then volatility is going to be larger. Now, when we have good news, all this part disappears. You see that? And we are left only with a GARCH, with a typical GARCH model. Make sense to you guys? So the conditions for this model is that if we have indeed leverage effects, gamma should be significant and gamma should be larger than 0. Now we have another model that is a Nelson model that also captures the leverage effect present in the data. Okay, the Nelson model, guys, is we're going to use exponents, natural logarithms. So for the Nelson model, what is beautiful is that we don't need anymore the non-negativity constraints because it's an exponent, ln. Right? So by definition, it's going to be positive. Right? However, as soon as this is a ln function, the time and the iterations that it takes to compute the results is longer. I will show you how this works in EVIOS. But the Nelson model, guys, now, it doesn't model sigma squared. It models ln of sigma squared of t. So we use ln, and this is going to be equal to omega. I will write the second part, beta ln of sigma squared t minus 1. And the way we model the leverage effect is going to be gamma that multiplies ut minus 1 over square root sigma square root of sigma t minus 1 plus alpha absolute value of ut minus 1 divided by sigma squared t minus 1 minus a correction factor, guys. This is basically the model. This is a correction factor. So forget about this model. It's a constant. Okay. So now let's take a look to what happens if ut minus 1 is negative. Okay, just follow mine and then I give you a couple of minutes to copy. So if ut minus 1 is negative, guys, so this implies the following. This is going to be equal to omega plus this part doesn't change. Sigma squared t minus 1 plus gamma. This number here is negative, so it's minus ut minus 1 sigma squared t minus 1. I will separate this one here, plus alpha, absolute value of minus ut minus 1, absolute value, square root of sigma squared t minus 1, plus, I'm sorry, minus alpha 2 over pi. So I don't care about this part. If we just focus on this part here, okay, so this is going to be negative gamma ut minus 1. Absolute value of a negative number is the same number, plus alpha ut minus 1 divided by sigma squared t minus 1 divided by sigma squared t minus 1. Got it? So now I will put the positive here, and I will put this something like that. So what I have here is going to be minus gamma plus alpha ut minus 1 over sigma t minus 1. Correct? And plus all the other elements are, I simply move all the other elements here. Okay. So this is omega plus beta ln sigma squared t minus 1. So this is ln sigma squared t. What is important here, guys, is that if we have leverage effect, of course, gamma should be again significant. And what should be the sign of gamma, guys? Positive or negative? What I want is this number here to be larger than alpha. Do you agree? So in order to be true, gamma should be what? Positive or negative?
Negative.
Negative. Why? Because if I have a negative gamma, negative times negative, positive, positive plus positive, a big positive. Make sense? So for the model of the Nelson model, gamma should be positive, gamma should be significant and smaller than 0. Copy, a couple of minutes, and then we do this in use.
Professor, question.
Yes, go ahead.
In the context of, let's just say, on a quiz or on the final oral exam, how would you envision test or quizzes on these concepts? Would you focus more on a concept?
I will focus on a concept and the knowledge of the model. So basically,
Thank you.
You should know this stuff.
Yeah.
No, I can present you this model. I don't want you to, you're not going to have even time to write, guys.
Right.
Got it? So, but for example, we talk about that later, but let's focus. No, what I want is the concept and understanding. So, and this is going to be a good exercise for you guys if you go to the industry and then you have a job interview. This is the type of questions they are going to ask you. Okay, everything that we have done in class is basically what these guys are going to ask you for entry to junior level position in a research institute or a bank or investment bank, whatever you're gonna see. That's what we do. Okay, so let's do this in EViews. EBS is extremely simple. So remember, this is my GARCH 1.1. So I don't need this one here. So let's do the TARCH or the Ggr model. Now, if you just go to estimate, the same quick estimate ARCH model, then I'm assuming that the RSP is that my returns on the SP500 are an R1 process. So this is my conditional mean. And then what I believe is that I have a leverage effects, and I want to model my leverage effects using the threshold or Ggr model. And this threshold order 1 refers to this coefficient, to the gamma coefficient, refers to this one here. Okay, this is what is called the threshold coefficient. Okay, so we have one threshold, and then we simply run and take a look to the results. Okay, guys. So the variable that we are interested is this one here: receipt minus 1 square, and receipt minus 1 minus 0. This is the variable that we're looking. So according to the threshold model, guys, what should be, first of all, my gamma should be significant. Do you agree? It is significant. Now, what is the sign of my gamma in order to have a leverage effect? Positive or negative?
Positive.
Positive. Exactly. Here's what we get. So indeed, we have leverage effects. So we have captured these asymmetric responses with this Ggr model very nicely. So we have a positive number here that is extremely significant. So this implies basically, guys, that the effect of the residuals is going to be, when we have bad news, is going to be not 0.01, it's going to be 0.01 plus 0.11. And you can see the difference. The volatility in the second case, it is 10 times larger than without good news. Agree with me, guys? Makes sense to you? So, and it is not insignificant. So if we fail to consider that model, take a look. Let's compare this with a GARCH, with a simple GARCH model. The model that the normal GARCH model, guys, tells us that when we don't consider the symmetric responses, apparently the good news and bad news, the volatility is influenced by 0.09 times the error square. You see, when there is no asymmetric responses. But when we see asymmetric responses, we can say that no, wait, this is wrong. When there are good news, the volatility reduces significantly. You just compare 0.09 versus 0.01. However, when there are bad news, the market overreacts very strongly, more than 0.93. It reacts basically on 0.12. Do you see that? That's exactly what we're trying to model, guys. We're trying to model this bad news. How important are bad news in the reactions of the market? Because those are the times, guys, in which you can take a position, either sell or buy, and take a position and basically make your decision based on these volatility changes. Now, volatilities are crucial, guys, also for options. So the price of options depend on volatility. So how do you compute volatility? Depends on where you are. You're in a bad situation. You're losing or you're making money. Okay, this influences your decision. Okay. Questions? Okay, so now let's do the Ggr model. The Nelson model, oh, by the way, guys, the Nelson model is also called Ggr model. So you have your model, and then when you want to select Ggr model, guys, you select Ggr here. So in the model, you select Ggr. And the symmetric, the delta that we use in the Ggr model, that is this delta here. This delta here. This one. Okay. is a Ggr parameter. This one here. So once you have your Ggr or Nelson model, GARCH 1, 1, and 1, then you are done. Here we are. What is this coefficient, guys? We need to be careful. C3 is a constant. Please pay attention here. C4 is not this one here. This is my X, right? C5. This is the one that C5 is the one that we're interested. Okay, is a residual -1 over the square root of the GARCH model. So C5 is a variable of interest here. Do you see that? Guys, so you see that? You see that this C5 is indeed this one here. Is mu t -1 over the square root of sigma squared t -1. This is what Evius calls GARCH. So if we go again here, here we go. Is this C5 the variable that I will be interested in analyzing? So now, guys, according to the Nelson model or Ggr model, first of all, this coefficient should be significant, just to prove that there are some leverage effects. And what is the sign of this one here?
Negative.
Negative. And exactly we have that coefficient. So this is negative and significant. So indeed, we prove again that we have leverage effects and that this model is going to be much better prepared than the simple GARCH model to do a financial forecast. The forecast, guys, that's as usual. So you go forecast and then you forecast the data you want, etc. We have done that in VAR. Okay, sorry, in ARMA type models. Make sense?
I just have a quick question.
Yes, go ahead, Giacomo.
Does the Nelson model, it doesn't have a null hypothesis, does it?
No, the null hypothesis, well, no, the null hypothesis from Nelson is simply, there is no null hypothesis. My null hypothesis in any case, if you want to take it, is that there is no leverage effects, okay? So if this number here is non-significant, for example, this implies that there is no leverage effect. So instead of using the Ggr or the Tgr or the threshold GARCH, just use the GARCH model.
Okay, thank you.
That's the difference. But in general, let me tell you, 99.9% of my life doing time series analysis, I never found that there is no leverage effect. And this is normal, guys. If you do some behavioral finance analysis, the people overreact more to bad news than good news. Okay, and that's, you know, humans are the ones that are working in trading, and even though machines are replacing humans on trading, algo trading, but who created the programs are basically humans. So you know, there is this type of bias in the results. Okay, make sense? Okay, perfect, guys. So let me stop share this one here, and then we go to a new model. So up to this point, what we have been doing, no, there is something more that is really interesting. So let me go here, first of all, before moving to the next step. So do you remember, guys, when you do portfolio theory, okay, so let's assume there is a very famous graph when we do this portfolio analysis. Here we have sigma, so this is volatility. And here we have expected returns. Okay, and there is a theory, guys, in portfolio optimization that tells you that we have something like that. This is the portfolio opportunity set. This is my portfolio opportunity set. But what is interesting about this portfolio opportunity set, guys, is the following. It shows you a very strong financial relationship here. The higher the expected return, what do you expect? The higher the volatility. Do it make sense? The more risk you're going to take, you're going to require more returns. Okay, this is a law. Got it? So now, if you take a look to your conditional mean, so I will write my conditional mean. I always write the easy way of writing this one here, guys. But remember, this is part of your analysis also. Okay. So determining the order of the number of lags, perhaps this is an ARMA 2 or whatever. You need to determine this model first. And then you model your conditional mean. Imagine like a GARCH model, that is the most flexible model. there is a way in which we can represent this relationship in the conditional mean. So what we do, guys, is we simply enter, I can do this, let's say, gamma. And then from here, what I can do is I can do two things. One, I can do the volatility, so this number here, the variance, or I can use the volatility. Got it? So this implies that I can have, okay, we'll write this explicitly just to be sure that you understand. So I can have this regression like that. Or I can write this one. Okay, and of course, sigma square. So this one here and this one here are modeled using a GARCH model. All right. So what is interesting here, guys, is the following. If volatility, more risk, increases, what do we expect? This to increase, correct? So by definition, guys, what we expect here is gamma is significant and gamma is positive. Agree with me, guys? Higher volatility, higher return. So my coefficient delta, gamma should be greater than 0. So if you do, just follow that, should be greater than 0. So this one here, guys, is called the price of risk. How much more you want to be making in order to get into a game that is more risky than another one? Okay. So let's take a look to how this works in EBUs. I want to see also that it's extremely simple. So GARCH in mean, I think, is this one here. Yes. So when you do the model, guys, the conditional mean is here. It's okay. And then next to it, you see arch M. You see this small part, arch M, to the right of the conditional mean. And then here is where you decide what do you want. You want the variance or you want the standard deviation. So the variance is the sigma squared t, and the standard deviation is sigma t. Okay, I will just use the standard deviation. Then my GARCH 1, and if you want a TARCH, perhaps let's put here a 1 or whatever. Got it? So you decide which model you want to use. And then simply let's run. Oh, what I've done. Oh, sorry. I cannot have this. I need to have the GARCH model only, not the TARCH model. So let me move this. Sorry, no, not TARCH model. Here. Now I can do this again. Here we go. You see, this is my delta, the one that I say the GARCH mean. This is called GARCH mean. So what do you think, guys? Is there a significant price of risk? Yes or no? This is the square root of GARCH, so this is my volatility. The higher the volatility, the higher my expected return. So it is significant, and also it's very, very strong. It's a very strong number. You see that? So this implies that risk indeed matters a lot, guys.
Professor, can you do me a favor and show me the estimated equation again?
Yes, of course. Here we go. So the model is exactly the same. Okay, I decide to use an Ggr, I use an Ggr, and the standard deviation as my metric for risk. And then I simply run. Of course, you can run if you want a GARCH model, for example, simple GARCH model, simply run. It's up to you, but remember, how do you select the model, guys? I'm not selecting the models here because it takes a lot of time. You use the Kaique and Schwarz criterion. First of all, you know that the GARCH model per se is not a good model, do you agree? Because we have shown using the TARCH or the Ggr that there are leverage effects. So this model here per se is not a good model. So you need to do, not progress. You need to simply do, okay, let's do a simple threshold model, 1, for example. And then you simply run this one here. And you can see here, guys, that the effect of the volatility of the conditional mean is significant and is very strong. Right? So this can be your best model, but then you need to start testing. So perhaps it's not an R1, it's an R2, for example. So you need to take R2, so you change this one here. Instead of R1, you simply start adding R2. Run. And then what you do, guys, is you compare your Ggr. Remember, we have done that in last class. And then what you try to do is you try to select the one that has the lowest Ggr. Okay, so that's what I've done here is simply I assume something that is easy to write, but in real life, guys, you need to be testing. Okay? But it is simple. It's really not complex. It's really not complex at all. Okay, good. So let's move then. I don't need this stuff. I don't need to save this one here. Okay, guys. Yeah, so let me show you now my screen. Let's do some theory about the things we're going to do now. So up to this point, what we have been doing is we have been working with a single series. Do you agree? Y, only one Y. Now, as you can see, guys, only one variable. Yeah, even though we have improved by using conditional mean and conditional variance, so we have improved the model significantly. But if you do the forecasts are not going to be really cool. You know, the forecasts are going to be okay, not so good, so. So what we're going to be doing now, guys, is why don't we use, instead of a single variable, we can use multiple variables at the same time, right? And so what we're going to do, guys, is what is called the vector autoregressive process, or what is known as Var model. It's called the Var model. V comes from vector, so we're going to have not only one series, but we're going to have two series or more. Now, what is interesting about this model here is that this is a multivariate model. What is interesting, guys, as you're going to see, is that all the variables are going to be endogenous. And this one here, and this condition here, guys, is crucial. If we had had time to do more multivariate analysis, multivariate or you know, another type of models, when you have endogenous and exogenous variables, you always need to find a way of balance the equation. You need to identify the equation. So having all endogenous, guys, simply implies that no need to identify the equations. So you forget about one big issue on multivariate analysis that appears when you have endogenous and exogenous. So the issue is that every single equation should have different exogenous. Otherwise, you're not going to be able to identify the system, right? But when everyone is endogenous, you forget about that. It's going to be extremely simple. No? What we have proved in literature, guys, is that these models here, these time series models are better than the structural models. For forecasting. Okay, so structural models are those models, guys, that you have endogenous and exogenous. Okay, in this case, any one is endogenous, so we forget about the identifying equations. And what has been shown in literature, guys, shown in literature is that indeed the forecast with these bar type models is much better than the forecast with the structural models. The problems, some problems, guys, is that it's tricky to interpret the coefficients. you're going to see in a couple of minutes, the model can get so overwhelming, so many variables, that if you want to interpret each coefficient, you're going to have a hard time, because the dynamics are tricky, and sometimes if you don't have a theory, because that's the problem with this one, is non-theoretical. It is based not on theory. Okay? So there is no theory that helps you to understand every single coefficient. You have the coefficients, but you don't understand what is the meaning of them. Right? So that's why these models, guys, are very useful for forecasting, not for trying to interpret every single coefficient. Right? How do we find, it's very, this was in the past. How do we find the number of lags, the optimal number of lags? Well, we're going to use again information criteria. I will show you how to do that in a minute. The other thing that you need to be careful, it's a problem, but also you need to be very aware of that, is that every single series that is present in your system must be stationary. Okay, so this model works with the stationarity data. It doesn't work with non-stationary data. Now, what is beautiful, guys, is that if you don't have contemporaneous regressors, in the left-hand side, no, sorry, right-hand side. So RHS is right-hand side. Then we use simply OLS line by line, or variable by variable. We use OLS equation by equation, say. Okay. So let's take a look to how the model works. Let's assume, guys, I will do a simple model. A VAR2 model. Okay. So a VAR2 model, these two implies number of lags, okay? And I will call a bivariate var model. So this implies bivariate means I have two variables, and the two implies number of lags. Okay. So bivariate means the following. So I have y1 at time t, and I have y2 at time t. Now, y1, I will write y1 first. So let's assume that this is y10 plus beta 1, 1, 1, y1 t minus 1 plus beta 1, 2, y2 t minus 1 plus gamma 1, 1, y1 t minus 2 plus gamma 1, 2, y2 t minus 2 plus my error 1 time t. Okay, so first, okay, copy, and then I will explain in a minute what's going on. So here I have the same. I will have here beta 2, 1, y2 t minus 1. Be careful, guys, that the terms are crossed here. Okay, so here is a 2, here is a 2 plus beta 2, 2, y1 t minus 1 plus gamma 2, 1, y2 t minus 2 plus gamma 2, 2, y1 t minus 2 plus u2t. Okay, copy, and then I will give you some intuition here. That is crucial. Okay, take a look to why this is beautiful. If we do an ARMA-2, for example, we should have this one, and this one. Do you agree, guys? However, what is beautiful about this one here, this model, guys, is that we have the interaction terms. These ones here, y2 influences y1 time minus 1. y2 at time minus 2 also influences y1t. Do you see? So there is this interaction terms between 1 and 2 that you can play with. So some information is going to come from y1t to y2t, etc. So they are going to be interaction. Okay. So, and that's the beauty about this one. So I will write this one here in a matrix form, just to show you how this works. So this is going to be like that. And then I will write all the betas, beta 1, 1, beta 1, 2, beta 2, 1, beta 2, 2. That multiplies y1 t minus 1, y2 t minus 1. Yeah, perhaps I made a mistake here, guys. Give me 1 second. Let me write this in a matrix form. T minus 2. No, sorry, guys, please pay attention here. Yeah, the way I written this one here should be beta 1, beta 2. This should be 1 and 2. Sorry, this one, there is no cross terms here. Let's do this. So this is, if this is those 2, 2, this is also 1, and this is 2. Okay, please pay attention here, guys. This is 1. Okay, from here we're gonna see why this happens. Okay, so let's start thinking about this. Are you with me, guys? Do you understand this model? So, a couple of things. This is going to be a 2 times 1. This is going to be a 2 times 1. This is going to be a 2 times 2. This is going to be a 2 times 1, 2 times 2, 2 times 1, and 2 times 1. Okay. Now there is a couple of assumptions here, guys. These ones here, each of them is a zero mean white noise process. And what is interesting is that the covariance or correlation between mu1t and mu2t equals 0. Okay, so there is no correlation, there is no covariance between these two guys. So these are the assumptions for mu. Now, if we call the bivariate model, so let's call it G. Okay, and the lags, we call it P, correct? So tell me how many variables we're going to, how many coefficients we need to estimate here in this 2 by 2? Well, I have 2 here, so it's basically G for this one here. I have G times G, correct? How many times? The number of lags. Agree with me or not, guys? How many parameters do we need to estimate? If I have a bivariate model, I need to estimate two constants, 2 y-intercepts, G. How many, my matrices, guys, are always G times G. So if it's a bivariate, it's going to be a 2 by 2. If it's a trivariate, it's going to be a 3 by 3. If we have 4 variables, it's going to be a 4 by 4. And how many coefficients do we have? As many lags as we have, correct? Guys, you agree? So basically, the total number of coefficients or parameters that we need to estimate is G plus G squared times P. So this is the number of coefficients. So this is what we have been calling always K. Now, how many parameters do you have, guys? Okay, example. Imagine that you have a trivariate var 4. Tell me number of parameters.
Four.
4? Very sure? So, okay, let's identify. G equals what? 4, right?
Yeah.
No, sorry, not 4, 3. It's a trivariate. G is the number of variables that I include in my series. G is 3. How many lags? P equals what? Where do I see the lags?
4.
4, this one here. Then, how many number of parameters I need to compute? Well, I need to compute 3 times 3 squared that multiplies 4. So this is 9, 36, 39. You see, guys? So the number of coefficients really increase significantly the more variables you use or the more lags you use. So that's why, guys, you need to be very careful. Normally, when we talk with var models, we try to find a parsimonious model. Parsimony means basically the lowest possible number of lags that you can compute with your model. Okay, that's parsimony. Now, how do we select the number of lags? As usual, guys, information criteria. Okay. The multivariate archaic information criteria is going to be ln of We can write this as sigma plus 2kt, my multivariate Bayesian information criteria, or Schwartz, ln of this one here plus kt ln of t, and the multivariate Han and Queen is going to be ln of sigma plus 2kt ln of t. Okay, as usual, guys, what you try is you try to minimize this one.
Professor, just another, I guess, more real-world question. Wouldn't it be intensely computationally expensive to try to go through a process of parameter tuning and find the lowest information criteria? Wouldn't that takes a long time?
Well, you know what? In my times, yes. If you talk about 10 years ago, even more, yes, it was very, it took a lot of time. Now, no. You know, I remember that the logic of having the lags comes from data. So imagine if you're using daily data, guys, you don't imagine having a memory of more than 5 days. So the lags 5 is more than enough. Remember, it's very short memory. If you have monthly data, 12 lags maximum. If you have quarterly data, 4 lags maximum. And it has an intuition. No? When you trade, guys, basically what happens is that you just focus Monday to Monday or Tuesday to Tuesday. That's your memory. You don't look for Monday 2 Mondays back. Okay, you don't do that. It's basically, the model is very simple. Now, this computer here, I have 16 gigas RAM. So it's a powerful machine. So running this stuff takes seconds. Mm-hmm. Now, if you use Amazon Web Services, the cloud, I used to do a couple of years ago, we did a huge simulation. We used more or less 40 million data points corresponding to 3 months data, tick by tick data of 30 stocks. So that was a huge and insane number of observations, and the number of models were not as simple as these ones here. And it took us, when I did something similar when I was doing my PhD in the beginning of 2000s, guys, it took me almost, I remember, almost 3 to 4 weeks to do that. Okay, with Amazon Web Services or any Azure or any cloud-based services, now it takes at least 1 hour and a half. You can see the difference. It is insane. If you do parallel computing, you divide the work in different computers around the world, and the results are there. So technically, and if you work for a bank, now the banks have the power to do this stuff. Make sense? So it's not so heavily complicated. Okay, guys. So we have how do we detect this one here, etc. Now, one thing that is really important. I don't know if I can do this here. Yeah, we'll try. Okay. I will tell you the following, guys. You just write based on this equation here. Okay, I have 4 hypotheses. The first hypothesis is lags of y1t do not influence y1t. Okay, so tell me my hypothesis is what? So I will do the following. So my hypothesis, if I want to test this hypothesis, what I'm saying, guys, is basically that beta 11 equals 0 and that gamma 11 equals 0. Do you agree with me or not? Guys, you agree? So if my hypothesis is that the lags of y1t don't influence y1t, simply what I'm saying is that beta 11, this one, is related to 1 y1t minus 1, and gamma 1 is related to y1t minus 2. So I'm saying that basically what beta 1 and gamma 1 should be equal to 0, correct? Okay, so now you do the following three hypotheses. Lags of y1t do not influence y2t. You tell me the hypothesis. The third one is going to be that lags of y2t don't influence y2t or y1t. And finally, lags of y2t don't influence y2t. Give me 1 second, guys. We'll bring some water. Okay, 1 minute to do this. You tell me, guys. So what is my null hypothesis here? Is not H1, it's H0. So if I believe that the lags of y1t don't influence the yy2t, should be, what coefficient should be equal to 0? First of all, I'm talking about y1t in the equation for y2t, correct? So I need to take a look to the second column, to the second row, right? So which coefficients are related to y1t in the second row? Beta 2,1 and gamma 2,1. Agree with me or not? Guys, do you agree? Perfect. So now, if we say that the lags of y2 don't influence y1t, so I'm talking about the first row, what are the coefficients that are related to y2, beta 1, 2, and gamma 1, 2. And finally, guys, the lags of y2 not influencing y2, I'm talking about the second row. And I'm talking about beta 2, 2 and gamma 2, 2. You agree? So the model is extremely flexible. As we're going to see in a couple of minutes, guys, the model is going to allow you to do a bunch of forecasting, to do a bunch of analysis, and you can say, you know what, I believe that one of the variables only influences the other one, perhaps the other one does not influence one, or perhaps both of them influence each other, right? Now, the first thing that you need to realize here, guys, is that we're not talking about causality, okay? We're talking about simply correlation, past information influencing current information, okay? So as you can see, this is all the right-hand side is past information trying to explain current information, right? So all these restrictions here, this type of relationship is past creating or influencing the present, not necessarily causality. Make sense to everyone? Questions? Yep. Okay. So let's take a look to the EBUS file that I sent you. You can open the EBUS file, the second EBUS file that I sent you. Where's my EBUS file? Oh, here we go. So the EBUS file that I sent you guys is called VAR 2007. Do you have it? Can you open, please? Do you have it, guys? Okay, perfect. So, okay, so the series that we are going to be working, the original series are these ones here, AOS. This is all ordinary stocks, shares. This is Australian index. And the other one is, what is my Dow Jones Industrial, this one here. Okay, so we can open both of them just to take a look to how they look. So let's take a look to block both AOS, DGI, open as a group. The sample is too small. I already reduced that. If you can do sample plus, I think we have all. Just here, remember, simply go here, write arroba all, just to have the complete series. I have selected AOS and DJI, Dow Jones Industrials. What's your hope in this one here? Let's take a look to the graph. Okay, clearly, guys, these two are non-stationary, right? So perhaps what we can do. Let me see. No, well, this is okay. So you see, guys, that they are not, basically, they're not stationary. Makes sense to you? Do you understand that? Okay, now, one common mistake of the people, guys, is that say, oh, you know what? Let's use the logs instead of the series in levels. So what I've created, guys, is you see L Laos, and you have LDGI here down. So if you just open one, take a look to the formula. Take a look to the formula, guys. It's simply the LAOS is simply the log of AOS. So you're just taking the log of the data, okay? And the people believe, I don't know why, and this is one mistake that happens very frequently, that taking the logs eliminates the stationarity issue. Okay, so let's take a look if this is true. It's open. It's a group. Give me 1 second. So let me name this one here. This is AOS. Oh, this is already. Yeah, forget about that. Yeah, so let's do the graph here. So, and let me name this one here as G. This is LAOS. And let me draw again the AOS with a DGI. 1 second. So this is a regular series. I will name it. G as graph is AOS Dow Jones Industrial. You see, guys, this is the log of this one here. Have we solved the issue of non-stationarity by taking the logs? Yes or no? No, not at all. Okay, not at all. The logs, if we use the logs, guys, what it helps us a lot is with the heteroscedasticity. Remember, when we have heteroscedasticity issues, one of the solutions was take the log of the series. Okay, it helps you with that. But in terms of stationarity, guys, it doesn't help you at all. It's a simple transformation. You see that, of course, take a look to the units. The units were in the thousands, and the logs are in the units of units. So it simply shrinks the data, but the properties are exactly the same. You cannot distinguish. If you don't see the y-axis, you cannot distinguish between them. Agree with me? So first thing to remember is that using the logs don't solve the issue of stationarity. Now, I will close this one. Do you remember one easy way to see if the data is stationary? We take a look to the correlation. So I will work with Laos, okay? I will just open one of them. And what I want to see is to see the correlogram. So I open Laos, and then I go view, correlogram. Okay, levels, 36 is okay. What can you tell me here, guys? Remember, the null hypothesis always goes line by line. So it is, there is no autocorrelation of order 1. Do you accept or reject the null hypothesis?
Reject.
No, reject. There is no autocorrelation of order 36. Reject. So this implies that we have autocorrelation for the 1, 2, 3, 4, 5, 36. Okay. Now, this graph here represents what? What type of model? Remember, the autocorrelation decreases, and partial correlation only has 1 and then goes back to 0. So which model looks? This looks like what? What type of model?
AR1.
AR1. However, guys, as you can see, the autocorrelation really continues even at 36 lags. So this is an intuition that indeed we have a non-stationary series. Okay, so this is visually one indication that, guys, you know what? I don't have a stationary series. Now, what I will do now is a test that we're going to use, a formal test that is going to help us understand if we have a stationarity or not. Okay, so let me move this here. So let's do test for stationarity. My test for stationarity, guys, is basically, remember when we had if I have an AR1 process, okay, so I say mu plus psi1 yt minus 1 plus ut. Do you remember? Which one was the coefficient that determined the stationarity, guys? This one here, do you remember? So we remember that if this number here is larger than 1, we have an explosive system. If this number was equal to 1, we have unit root. Guys, give me 1 second, please. Okay, this is it. And then if this number, if this coefficient here was small in absolute value, okay, in absolute value, yeah, this should be absolute value. Absolute value is smaller than 1, so we have a stationary process. Do you agree? So the test that we're going to be using, guys, is called the Dickey-Fuller. Now, and augmented Dickey-Fuller also. And the basic idea is very simple. Take a look to what I do. So I have 3 models, guys, but the basic one is going to be this one. Yt equals psi yt minus 1 plus ut. So what is the null hypothesis here, guys? If there is non-stationarity, what I assume is that psi equals 1, correct? So that the null hypothesis is going to be that the series are non-stationary. Please remember that. So the series are non-stationary. Now, yeah, we can obviously do a wall-type test for checking that psi equals 1, but we are not used to work with psi equals 1. Do you agree with me? So what I will do is I will do a trick. I will subtract this one here. So I'm not changing anything here. So this one here is going to be change of yt equals psi minus 1 yt minus 1 plus ut. And I will call this one here, and this is the model. I will call this one here psi of yt minus 1 plus ut. So now my null hypothesis, guys, is simply that psi equals 0. Okay, 0 implies non-stationarity in this case. You agree with me, guys? Because psi gets 0 when psi equals 1. So if this is 1, all these coefficients psi, big psi, equals 0. Right? So this is normally the equation that the EViews or any other packages use, guys. Okay, so remember that the null hypothesis is that the series are non-stationary. Okay, please remember, series are non-stationary. This is the null hypothesis. Now we have 3 cases, as we're going to see in the test, in EViews, there are 3 cases. Okay, let me explain the 3 cases very quickly. The first case is this one here. So my null hypothesis is going to be yt equals yt minus 1 plus ut versus yt equals psi yt minus 1 plus ut. So basically here, psi is smaller than 1. So basically here I'm saying unit root. So remember, unit root is non-stationary. Okay, so this is case number 1. Case number 2, guys, is what I do is I simply introduce the intercept, the drift. My model is going to be mu plus yt minus 1 plus ut. So this is versus yt equals mu plus psi yt minus 1 plus ut with psi less than 1. So this model here is a model with drift, R1 with drift. And the last case that we're going to be seeing in EViews, and we're going to describe this in details, guys, is my H0 equals yt equals my drift plus my R plus, let's call gamma t plus ut. Okay. So this is called R1 with drift and trend. That is also non-stationary. Versus my drift plus the coefficient versus this one is smaller than 1. Okay, so these are my 3. These are going to be my three. What do I call it? My 3 hypotheses that I will work with. Okay, copy and you will see how the application works very simply. Okay, guys. In a couple of minutes, I will show you how to do that. What I need to do, guys, is I need to do another video for this part here for you. I will detail the EView side of the equation. I will start doing some of the Beck model. And I will be sure that you have this video by early Saturday, so you can review before class also. Make sense to you? please review. I need to talk a couple of minutes about the next quiz. The next quiz, indeed, actually, guys, I'm thinking that if we do today, I do the video about finishing this part of the VAR that is very simple. I can explain this to you in 30, 40 minutes maximum. Then I can start doing the back model. So on the 4th, we're going to finish the back model. But what I will do is I will create for you the videos for the VAR, this model. And I also will create the videos for the back model. So we have basically all the classes ready for Wednesday. And Wednesday, what I will do is I will do a review of everything. So I will put you in perspective, everything. And so you're going to be ready for your test. Remember, your test is going to be on the 7th, Friday, the 7th of May. I will provide you the test at, let's say at 6 p.m. And then you need to return to me on Saturday before 8 in the morning. So you have all the night. And actually, I believe that we're going to have 2 tests. We're going to have test number 2 and 3 and 4 at the same time. Okay, so you're going to have 2 tests. Okay, and the same day. It's going to be, because everything is related. The first test number 3 is ARMA and GARCH, and test number 4 is VAR and BEC that we're going to be seeing. Everything is already in place. You're going to see it's very simple. Okay, guys. So we need to stop here because I need more time to show you. I will prepare for you what is next on the videos. Please, as soon as I send this to you, review them, listen to them, understand them, and on next Tuesday class, we are going to basically go over the examples and you explain you the details, etc. The final exam is the final exam is going to be on the 11th.
Professor, quick word after class.
Yes, of course. Okay, guys. So we see you soon.
Thank you.
Okay? See you guys. Take care. Good night. Take care.